Hey, what's up, guys? Yeah, so it's a little bit long time for me to film this Galois theory series. Yeah, so today let me just talk about the important theory in the Galois theory, and then once we prove this, then in the next video that we can start to prove the Galois main theory. Okay, so I would say this theory is the starting point. Okay, so remember that we have right, so remember that somebody give you the field extension, let's say k over f, let's say suppose this is finite extension, and we have proved that finite extension leads us to the algebra extension. So actually, and then we can define a so-called Galois group k over f, which is all the automorphism from k to k such that it fix f. Okay, so this is automorphism. And so we also have a dimension. So what is the relationship between the dimension and the Galois group? So this is a theorem. If we have a Galois group K over F, this Galois group must be finite, and this order is bounded by this K F. Okay, so that's equal to. And then in the normal, if you further assume that K over F is a finite Galois extension, then in the next video we will prove that there will be an equality sign. Okay, so let me just write down. So if K is a Galois over F, then equality holds. Okay, so this is the powerful theorem, right? Otherwise, that nobody knows Galois group is, right? Because when your K become complicated, or your K come from some polynomials, some roots of polynomials over F, then it's very hard to compute a Galois group in general. So, but this theorem tell you like the simple bounds to bound the Galois group. Okay, so lemma. So this lemma is like a linear algebra effect. So let me just quickly say it. It's not difficult. So K is a field, and K is a field. And then that's sigma 1, sigma 2, up to sigma n are all distinct automorphism, all distinct auto over K of K. So you take K from K, K to K, and then you take the n distinct automorphisms. And it's impossible to find the A1, A2, up to AN, not all zero. Okay. So theorem says that you cannot find the solution such that A1 up to AN, which is not all zero. Such this coefficient lies in K, such that A1 sigma 1, A2 sigma 2, AN sigma n, this guy acting on a U equals 0 for all U belongs to K. Okay, so this is like the no-go theorem that you cannot find the n different numbers, which is all non-zero, such that a linear combination with this automorphism acting on U is 0. Okay, and yeah, okay, so let's go to a proof. Okay, so so the idea proved by I think it's the induction, right? So okay, so let's do this. Okay, so let's first do this. Okay, so let's prove by contradiction. Contradiction. Okay, so suppose in the beginning that somebody handing you all the non-zero of it, then I can, if there are zero of it, I can just delete it, right? So I can say that, oh, so I can assume that I got the equation like this, and all the AI up to m are non-zero. Okay, and then we want to prove that this is impossible. Okay, so first, let's consider a case if m is 1. Then I got one sigma A1, A1 sigma 1 U, which is 0. Okay, so this is impossible, right? So this is impossible because A1 is non-zero, so sigma U is 0, right? But this is for all U, right? So if you put U equals to 1, and then contradiction, okay? And also notice that sigma 1 is different from sigma n. So there exists the C belongs to K, such that sigma 1 C is different from sigma m C. Okay. So I can take this equation as acting on the CU. So I can acting on, let's say, acting on the equation, acting on the number called CU. C is a number in K, C is in K, and U is in K. Okay. So I take the A1 sigma 1, and I use the property of the automorphism. So I get the sigma C, sigma 1 U, A2 sigma 2 C, sigma 2 U, AM sigma MC, sigma MU equals to 0. Okay. And this, okay. And okay. So from this and compare to this, right? I times the sigma 1C in this equation. Okay. Okay, so I take the sigma 1, I times the sigma 1C into this equation. This equation, let's say this equation act on U, then I will get the A2 sigma 1C. Sorry, this is A2, and the sigma 2, sorry, let me just write down. So this is A1 sigma 1 U, A2 sigma 2 U, up to AM sigma MU 0, and I times this equation by sigma 1C. Okay, so this turns A1 sigma 1C, this is A2 sigma 2U, sigma 1C, and up to AM sigma MU, sigma 1C equals 0, and let's do the difference. Okay. Okay, so you see the first term cancel, right? You get sigma 2C minus sigma 1C, and sigma 2U plus A3 sigma 3C minus sigma 1C, sigma 3U, to AM sigma MC minus sigma 1C, sigma MU equals to 0. Okay. Okay, so you can take that. Let's say I take BI equals to AI sigma I C minus sigma 1C. Okay, so I get another equation called B2 sigma 2, B3 sigma 3, up to BM sigma M is 0. Okay, and all the BI. Okay, so notice that okay, so let's see, right? We have this, and obviously that BI are in K, right? Because all these are in K, and we know that AM is non-zero, right? So which tell you that okay, so which tell you what? Okay, yeah, that's so. That's okay. Okay, so what we got? Okay, so what we got? So what we got is a strange situation, right? Because originally I can somebody handing the equation to me, right? I can delete the 0 terms and take out this. So let's do this imagination. Let's say somebody that let's say I take the omega, I take a set of omega such that it's A1, A2 up to AN, A1 sigma 1 up to AN sigma N. Let's say I take this is all these are all non-zero, or all non-zero. And I'll take out this and this kind of 0, right? Suppose this is a set of omega, then I can take the minimum. I can take the shorter length such that this equation holds. Okay, and we prove that this equation cannot hold for m equals to 1, right? So basically, you at least should be 2 of them. At least the length should be 2. Okay, so which tell you that you can take, let's say I can take m to be the minimum length in omega, right? Because this is a finite length, right? So we got some finite. Okay, but if from this computation, then I can get something which is shorter than original length, and this guy is also a valid equation, right? Because Bn is non-zero. So now I produce the shorter one. I can say that m is the shortest one. And now I use this field property, and I prove that there is a shorter one, right? So this is contradiction. Well, this proof is very very intriguing. It's not difficult, right? But just you need to think a little bit. Okay, so now we can go to this theorem. Okay, so our goal is to prove that let's say K is a finite extension over F. Maybe sorry for my sometimes changing notation. And then we want to prove that the Galois group K over F, its order is less or equal to Galois the finite the dimension of the field extension of K over F. The proof is not difficult. Let's say K over F is in. Okay, so which means and right. So let's say U1, U2, UN as a basis. Okay, and we want to prove this, right? So let's prove by contradiction, right? Suppose we have n+1 distinct automorphism K to K, which fix F, right? So let's say sigma 1, sigma 2 up to sigma K, sigma n+1. Okay. Okay, in the let's say Galois K or F. Okay, so these are, so if I forget about a fixed F, then I can say what? These are all the general, just linear transformation, right? So I, in a n-dimensional vector space, I take n+1 invertible matrices. So there must be what? There must be some non-trivial solution, okay? So there is this, so from linear algebra. So we have n+1 invertible matrices, right? So there exists x1, x2, xn+1. I should say not all 0, so not all 0, such that sigma 1 u1 x1, sigma 2 u1 x2, the sigma n+1 u1 xn+1 equals 0, and then you get sigma 1 ui, let's say x1, sigma ui x2, so sigma n+1 ui xn+1 equals 0, and finally sigma 1 un x1 sigma 2 un x2 up to sigma n+1 un n+1 equals 0. Okay, so this is the linear algebra fact that you take n+1 invertible matrices and invertible linear transformation in the n-dimensional vector space, right? Then you can find a solution such that you put it, right? So this becomes just some coefficient. Okay. Okay, so which tell you what? Which tell you that if you combine it, and okay, so I should say this is a linear system, right? So there is a non-trivial solution. Let's say A1, A2 up to an+1, such that all of these satisfy. Okay, so that means what? That means you can see that A1 sigma 1 ui plus A2 sigma 2 ui plus an+1 sigma n+1 ui is 0 for every I. Okay, but this I is a basis, right? So which tell you that you prove that A1 sigma 1, A2 sigma 2, an sigma n acting plus an+1 sigma n+1 u is 0. Okay, for every u belongs to K. Okay, but what? But if you can find these things, then you violate original constant or the lemma, right? So you violate the lemma. Okay. Because in this case, that all your A1 up to n+1 are non-zero, right? But all of these are K automorphisms. Okay, so which violate the lemma. Okay, so which means that we prove this theorem. Okay, in the next video that I will start to prove the Galois main theorem, and then we can go to the solving equations. We can just talking about how the normal extension fit into this discussion. Okay, so but I think this is a very important theorem, right? So basically, let me just discuss, right? So for example, Like this, for example, this, right? You know that this is, you know that the q squared root of 2, this is 2, right? So would you can prove that this is greater than the Galois group of q squared root of 2 over q? Okay, so which this is indeed Z2, right? So actually this can give the powerful bound to bound the Galois group. Okay, so see you guys next videos.